These endlessly long black cables, seemingly harmless, are actually holding the fate of tech giants like Google and Facebook in their hands. Yes, undersea fiber-optic cables, an almost invisible infrastructure system, transport over 95% of internet traffic, connecting trillions of bits of data from Asia to the Americas while resting on the ocean floor. It is incredible to think that this global connection originates from glass strands thinner than a human hair, crafted from tiny grains of sand in state-of-the-art manufacturing facilities. So, what technology transforms these delicate glass fibers into cables robust enough to span entire oceans? And more importantly, how do we lay thousands of miles of cable on the seabed and keep them there for decades? Let's find out. You have likely heard stories about sharks biting undersea cables and causing internet outages. Yet, it is only when a cable is actually severed, slowing down connections and disrupting a host of services, that we realize something astonishing: just how heavily modern civilization relies on these strands lying deep on the ocean floor. If you had to go 24 hours without the internet, do you think you would be okay? As for me, I would probably go crazy. Today, over 1.5 million kilometers of undersea cables crisscross the oceans, acting like the circulatory system of the digital world, to transport the vast majority of international data between continents. And as the artificial intelligence era drives a surge in data demand, these cables have become absolutely indispensable. To better understand how fiber-optic cables actually work, let us first examine their internal structure. Beneath what appears to be a simple outer casing lies a multi-layered structure engineered with extreme precision. At the center is an ultra-pure glass core, where data is transmitted in the form of light. In single-mode fibers commonly used in telecommunications, the core measures only about 8 to 10 micrometers in diameter, far thinner than a human hair. Surrounding the core is the cladding, which keeps the light contained within the fiber rather than allowing it to escape. Next come polymer layers that protect the glass from moisture, scratches, and microscopic cracks. Multiple color-coded fibers are housed in water-resistant tubes and twisted around a central strength member. The assembly is further reinforced with aramid fibers, steel wire, or metal armor before being encased in a protective plastic sheath. From a strand of glass thinner than a human hair, successive layers of material transform it into the nervous system of the digital world, spanning cities and stretching across the ocean floor. Now, let's look at the manufacturing process for glass optical fibers. Everyone knows that glass can be made from sand. However, ordinary sand is insufficient for creating optical fibers. Optical fibers require ultra-pure silica, typically with a purity level exceeding 99.99%, because even minute amounts of impurities can absorb or scatter light, causing the signal to weaken over long distances. Subsequently, high-purity sand is fed into an industrial furnace at a temperature of approximately 1,400 degrees Celsius for 24 hours to form a large glass rod known as a preform. The preform rod is then inserted into a hollow silica tube, approximately 1.8 meters long, that rotates continuously on a lathe. Simultaneously, a flame reaching 2,000 degrees Celsius moves steadily along the tube's surface. Inside, vaporized precursors react and deposit an ultra-thin layer of silica onto the tube's inner wall. A layer so thin it is virtually invisible. However, over the course of hundreds of deposition passes, spanning roughly 8 hours, these microscopic silica layers accumulate. The hollow interior gradually fills in, forming a solid glass structure. Once the layers reach the required thickness, the temperature is raised further. The white silica layers turn transparent, while the central hollow space shrinks until it vanishes completely. By the end of the process, the original hollow glass tube has been transformed into a solid preform rod several centimeters in diameter. While it is not yet an optical fiber, the entire structure that dictates the path of light has already been precisely defined within this glass rod. Next, engineers must transform these glass tubes, measuring a few centimeters in diameter, into optical fibers with diameters 100 times smaller. To achieve this, the preform is suspended at the top of a drawing tower and slowly lowered into a furnace heated to approximately 2,000 Celsius. At this temperature, the lower end of the preform softens and stretches into a molten glass drop. Tractor wheels at the bottom grip the tip of the fiber and accelerate, pulling the large glass rod into a strand with a diameter of about 125 micrometers, thinner than a human hair. From there, the optical fiber races down the tower at speeds that can exceed 3,000 feet per minute, approximately 900 meters per minute. The higher the speed, the more difficult it is to maintain a uniform fiber diameter. Consequently, laser sensors continuously measure the fiber's diameter during the drawing process. If the fiber is slightly thicker than the standard, the tractor wheels immediately accelerate. If it is too thin, the system instantly slows down to bring the diameter back to the required level. The optical fibers, freshly drawn from the preform, immediately pass through a camera and sensor inspection system to detect deviations in diameter or coating, as well as any microscopic cracks. Next comes the proof test, where the entire fiber is subjected to a tensile stress of approximately 100,000 psi to verify its strength. Any section containing a defect will snap immediately and be discarded, while the segments that meet the standards proceed to the next stage. After passing inspection, the transparent optical fibers appear virtually identical. Consequently, they are fed through a coloring head, where an ultra-thin layer of ink is applied and immediately cured using UV light. Typically, a standard 12-color system is employed to enable technicians to distinguish individual fibers during splicing or repair operations. Following the coloring process, the differently colored fibers are fed into a common production line, where they are bundled and twisted into a specific configuration. This arrangement keeps the fibers organized and prevents excessive tension when the cable is bent. At the end of the line, the fiber bundle is continuously wound onto large cable reels, ready for the subsequent application of water-resistant, load-bearing, and protective outer layers. After being dyed, the fiber strands are transferred to a twisting machine. Here, multiple optical fibers are simultaneously unwound from their spools, gathered, and twisted into a specific configuration to form the cable core. This core is then wound onto large reels, ready for the subsequent stages of reinforcement and protective sheathing. These cable cores are then moved to the reinforcement and protective coating line. This is the stage where the delicate bundle of optical fibers truly transforms into a cable capable of withstanding the harsh conditions of the ocean floor. First, water-resistant and load-bearing layers are added to the core. These prevent moisture ingress and protect the optical fibers from strain when the cable is under tension. Next, the cable core passes through a high-speed winding machine. Dozens of ultra-durable aramid strands are evenly wound around the core, alternating between yellow and black to allow operators to easily monitor the winding direction and distribution, as well as detect any irregularities during production. This reinforcement layer helps distribute tensile forces, Consequently, when kilometers of cable are subjected to tension during transport and subsea deployment, the internal glass fibers do not have to bear the full load directly. Once manufacturing is complete, the fiber optic cable embarks on a completely different journey, being laid on the ocean floor. First, the cable is coiled into massive circles within specialized storage tanks, layered continuously from the outside in. This arrangement allows for the storage of immense lengths of cable while ensuring it can be paid out smoothly without twisting or tangling. From there, the cable is loaded onto a specialized cable-laying ship and stowed in large tanks within the hull. A single vessel can carry thousands of kilometers of cable, along with the equipment needed for a voyage lasting several weeks at sea. As the ship heads out to sea, the cable is gradually paid out from the storage hold, passing through a system of guide wheels and tension control units before entering the water. The payout speed must be constantly adjusted to match the ship's speed and the water depth, as excessive tension could damage the cable. Next, a specialized robot-like machine known as a subsea cable plow is lowered to the seabed and towed behind the vessel. As it moves, the plow's forward blade cuts into the sediment, creating a narrow trench. The cable is guided through the machine's internal system and laid directly into the trench. The displaced sediment then gradually settles back over the top, concealing and protecting the cable from ship anchors, fishing nets, and other near-shore hazards. However, not the entire length of a transoceanic cable is buried in this manner. When the ship reaches very deep waters, where the risk from anchors or fishing activities is virtually non-existent, the cable is typically laid directly onto the ocean floor. In this way, the cable-laying ship continues its journey, while beneath it, the specialized machine precisely places the cable along the pre-surveyed route. And that is how a massive undersea fiber-optic cable network spanning approximately 1.5 million kilometers was manufactured and installed. Do you find the journey the internet takes to reach you to be a complex one? Thank you for staying with Mido Explained until the end of the video. If you found this interesting, please give it a like. Goodbye for now, and see you next time.